begin tonight's stream with several moments of calm and meditative state. Because what we are going into, we are going to go deep down the rabbit hole. But do we really need to? That is the question. And I have the answer. So, as I progress through my journey, I'm making some interesting discoveries about light. So one of them is that we're always taught to believe that the speed of light is a certain speed, 300,000 meters per second, whatever it is. It's a really fast number. But believe it or not, what they've been teaching you in physics all these years is wrong. That is not the speed of light. Now, I'm just gleaming this information over the last couple of weeks as I'm building this project. I've got over 50 years of physics and electronics education and experience, and you gotta know some of this stuff, you know? But there are some things I don't know, and in order to progress through my particular journey as to what I'm doing with my project, it would be somewhat helpful to understand the true nature of light. So, the truth is, not the fact, but the truth is that actually, let me just look this up here. Let's just go to our little wiki. I was going to say something else. Oh! That would not have been very good. Let's see here. The speed of light as we meditate. According to most physics books, etc., the speed of light equals 299,792,458 meters per second. You can convert that to kilometers, and it comes out to approximately 300,000 kilometers per second. This is the so-called speed of light. What is the speed of light? This is what the AI tells you. This is the ChatGPT. This is the physics. This is all these things you've learned over the last frickin' 100 years. This is what they tell you. This is the speed of light. I got news for you people. Listen to me. This is not the speed of light. This number is the maximum speed of light in a vacuum. What does that tell you? That is an enormous statement that should have been made 100 years ago. And it was never made that. In all of these calculations and all of these studies and all of this research and all this crap, they teach you this number is the speed of light, and it's wrong. And I'm gonna give you the information you need to make that decision for yourself. I'm not here to prove anything. I'm not here to disprove anything. I'm here to look at the facts and take the scientific facts and present them as possible truths into the nature of light. We're going to start from the basics. We're going to work our way up to the mid-level explanation of things. And it looks like there's some pretty good videos that teach all that. And okay, yeah, somebody might come in and might say, oh, we know it's not the speed of light because when you put it through water, it slows down. Well, I got news for you, Bubba. When the light comes back out of the water, what does it do? It goes back to the speed of light, which is 300,000 kilometers per second. Wow. Wrong. I'm going to present to you a formula that's used to calculate velocities, okay? And let's see, let me do this here. And there are some certain things, there's some certain things that happen. So we're going to talk about radio waves. And what we're going to do is I'm going to go ahead and take this music and I'm going to bring it down a notch. That's pretty good, I guess. I'll go ahead and bring up, well, I've got YouTube set up, but I don't have web page, and I probably could just, well, there's this here. Let me go to properties, and we'll bring up, oh, well, it should be filtered out, of course. So we'll go ahead and get rid of the pyramid. And now we've got our web page, and it's all illustrious form here. So we're going to start with radio waves. Actually, you know what? We're not even going to start with that. Wait just a moment here. Let's see. We're going to start with what's called the radio spectrum, and we're going to go to images. And let's go ahead and use this image. And what I will do is I will actually we'll save this image, and we'll put it in pictures. We'll put it as spectrum. That way, when I load it up, I can bring it up as a larger picture. What did I just do there? Let's go ahead and do this here. Go to pictures and find spectrum. And we'll open that up with the program that's called whatever Windows is. Let's see. We got video capture. We got YouTube. We've got. Why does that do that right there? Come on, get out of there. This picture view. And that will be okay. Good. And so I'm gonna adjust this picture here. This picture view a little. So always things that we have to do in the stream to kind of. So what we have here is called the spectrum, the radio spectrum. And as you can see, the visible light in the middle is part of the radio spectrum. We've got, it's kind of backwards actually. I wish that the lower frequencies were on the left. They should be on the left and then go from left to right, but this is going from right to left. Okay, we live in a backwards society. So starting from the left and going beyond the left, we've got AM radio. So if you tune around on an AM radio station, you might hear these little whistle sounds. That's called the carrier wave. It's an amplitude modulated carrier wave, and it's called double sideband, and you hear the audio that comes through the AM radio. It's down around 500 to 1600 kilohertz. Okay, that's a frequency, and I'll get into that in a little bit. Yes, we're going to go into some equations. So below the AM is the audio. Audio is 1 kilohertz to 10 kilohertz, 1 kilohertz to 20 kilohertz. It's in that frequency range. We're going to talk about frequencies first, okay? So it starts there. It starts in the audio. When you listen to a radio station, the receiver takes out the carrier wave and it provides you the information, which is the audio. That's like 4 kilohertz, for example. So the sound bounces back and forth between the invisible carrier wave and the limit of the audio frequency, which is like 10 kilohertz, whatever. It's in that range. So that bounces around and you get audio information, music, speech, that sort of thing. Now, there are many different modes of communication. There's Morse code, there's ASCII, there's Bardo, there's radio teletype, there's packet, there's different types of communications. And I need to have a good handle on that. Now, there's software that can decode much of these types of transmissions. And there's a software that does something else really, really strange, which I discovered playing a video game. Okay, this is coming from a video game, people. You can learn things from any source if you put your mind to it. So, Elite Dangerous they devised a series of audio signals coming from these little cubes and stuff out in space. And what they discovered these pictures coming off the audio waves. And I'm like, how the hell did they do that? What is this all about? This is a picture coming from audio. And there's other signals. There's slow scan TV. There's some other visual things that come from higher frequency audio waves. But this is not that. This is a low frequency audio wave, like me and you talking. And you can hear it. It makes this noise. But when you decode the noise, there's a picture embedded. And I don't mean just a picture. There is some detailed information in these pictures coming from this audio wave. Now, it's possible that we can collect some noise information that we don't understand what it is. If we listen to it and hear the sounds of what these things make, when I go and do my final tests on my equipment, I can say, hey, I know what that is. I know how to decode it. Okay? So that's that aspect. That's the audio. So those are the low frequencies. Then you go up to the amplitude modulation, AM. Then you go to the FM. So we start from right to left. Then you go to TV. It's up to, I forget the frequency now. And then you got radar. Then you've got the gigahertz range. You got megahertz is your shortwave radio from 1 megahertz up to 30 megahertz. Then you've got your 2 meter, you get your 50 meter band, which is up to 50 megahertz, and then you get the 2 meter band, which is up to 140 megahertz. So you notice the meter size goes down as the frequency goes up. Now they're not showing the frequencies here. So then you've got, it seems like you have a fairly wide range of infrared, which is not visible. Then you've got the visible light, which is a small portion here. And you've got ultraviolet, X-rays, and gamma rays, and so on. If you notice on the top, you see this waveform. And what this is the wavelength. This is the length from peak to peak of the waves at those frequencies down below. Now, the wavelengths have a measurement. So when you go from right to left, it's like 1 meter, 1 centimeter, 0.01 centimeter, 1,000 nanometers, 10 nanometers. You know, the wavelength gets smaller and smaller and smaller as the frequency goes up. I guess visible light's in like the terahertz range or something. So you have frequency. Now, what you also have is you have waves. Now, we know about the discussion of particles. My feeling is that particles are not waves. Particles carry the information to make waves. Particles have a wave-like nature, but they are not waves themselves. But what's really weird is that one particle contains all the information of the entire wave. Okay? Go figure that. That's go figure that right there. One particle, one photon has all the information. How do I know? How is the proof for that? Because all the other photons that go in fill in the gaps. How do they know where the future photon went? He can't see it. It's because it's going at the speed of light. It's going too fast. All these things are happening at the speed of light. These little photon things are just bouncing up the wall, creating this wave. And so I say that each particle, whether it's an electron or photon or whatever, has all the information of the wave that it eventually creates over time. So just keep that in mind. So then we've got wavelength. Okay, so we're going to go ahead and I'll minimize that. And let's go back to my video section here. I think there was a video, it was this one here. The electromagnetic spectrum song. What is that, I wonder? Alright, we're gonna go ahead and pause the music.
A range of radiation, let me tell you what.
Okay, we're not gonna listen to that bullshit. So if we go, this is called a radio spectrum. And so radio waves, when you go from a transmitter to the antenna, it goes through a cable, okay? Now, it doesn't go at the speed of light. It goes at a fraction of the speed of light through the cable. This is called a velocity factor. So we'll go ahead and look up velocity factor in Wiki. And we'll see some information and so on and so forth. And we'll just kind of keep cruising down. And each different type of cable has a certain velocity factor. That factor is a certain percentage of the speed of light. Now, velocity factor is an important characteristic of communication media, etc., etc. Typically has a velocity, a plenum data cable, which is 42% to 72% of the speed of light in a vacuum, and a riser cable, so on and so forth. So RG8U is an example of a radio cable. I'm an amateur radio operator, so I know all about these cables and stuff. I'm surprised that the velocity factor is a lot lower in some of these. These are wires, okay, versus these cables. So RG8U, I got RG8AU. Well, the RG58. Okay, so around. You can use a smaller cable at higher frequencies, I think, and the bigger, fatter cables, which is the RG8, you use it at lower frequencies because of the wavelength of the it's the wavelength is longer. Well, that's okay. Oh, those are network. Okay, that's network. Well, they don't use RG8 for a network. That's stupid. Okay, so radio communications provides this table here. So there's RG8. I don't see RG213 is supposed to be better, but I guess it's not. It's down to 66%. It's supposed to be RG8AU, but I don't see it in there. All right, so here we got some formulas. All right, so in the cable, we have what's called permeability. It seems like there's a dielectric constant, or relative permeability is a factor that is inherent in the cable. There's a dielectric constant. It has to do with capacitance and resistance and so on and so forth. This formula here, Vf equals 1 over the square root of UR epsilon R, that's the formula for air, I think. That's the number that you use to guide everything by relative permeability. And they're talking electromagnetism, okay? Just keep that word in mind. And so then they've got some formulas for the inductance and the capacitance of the line, and it will give you a velocity factor, and that's multiplied by the speed of light. It tells you how fast, that's the velocity. It'll tell you how fast that radio wave is going through the line. Now, light waves don't go through a solid line, okay? There's also propagation delay, which is kind of interesting. Let's look at that. So electromagnetic wave traveling through a medium has a propagation delay determined by the speed of light in that medium. So there's gate delays. That's sort of interesting.
Oh, so much for that.
So they talk about the speed of sound. Remember, I was just saying the speed of light is a certain number. Well, then the speed of sound is a certain number too. Then that number is not the speed of sound; it's the maximum speed of sound. And so maybe you can change the speed of sound. So the speed of sound in dry air is at a certain level. The speed of sound in an ideal gas depends only on its temperature and composition. 343 meters per second in air. Air at sea level, 331. Air density changes as you go up. Sound travels mostly slowly in gases, faster in liquids, and fastest in solids. For example, while sound travels 343 meters per second in air, it travels in fresh water, it travels 1,481 meters per second. I didn't know that. But it's still the same frequency. Okay, it's the same thing with light. Light has a frequency. Radio waves have a frequency, and that's determined by the wavelength and so on and so forth, etc., etc. Sound waves in solids are composed of compression waves, like gas and liquids, and a different type of sound wave called a shear wave, etc. only occurs in solids, so on and so forth, yada yada, yada yada yada. Compression and shear waves. I got quite a discussion here. And some derivatives. Altitude variation, implication, atmospheric acoustics. Ideal gas pressure. We don't need to get into that. Yada yada yada. It talks about density, so on and so forth. A lot of this stuff that pertains to much of this stuff that pertains to sound does not pertain to air. Um, but one of the things that does is wavelength and frequency. So let's just go ahead. We've talked about the velocity factor. So now we've said that this is a maximum. So that means light can travel at a slower speed. When light goes through through water, it travels at 200,000 meters per second, or 200,000 kilometers per second. But when it gets to the end, and it comes back out the water, it jumps back up. So what happens is it compresses. Somehow it compresses at the end, and then it just boom, it just pops out at that speed of light again, which is problematic. Meaning I was thinking, I could slow the speed of light down. I would have to encompass my entire project inside of liquid in order to, excuse me. So anyway, there's that story. So let's go back. I wanted to look up the formula. I wanted to go, let's see, formula for wavelength. All right, so this formula right here, lambda equals V over F. Lambda is a wavelength, V is a velocity, and F is frequency. So you actually have the speed of light as V, and then you can see if when you're going through a medium and the velocity, which is the speed of light times the velocity factor, is now going to change the wavelength, even though the frequency is constant. Or the frequency and the wavelength become independent of each other in order to maintain the speed of light. Don't really know that. I don't know. Who cares? Lambda, wavelength, velocity, meters per second, frequency is in hertz. And so you run this through, and for example, without looking at that bottom stuff down there, 4 megahertz is the 80 meter band, and the CB band is the 11 meter band. 11 meter is the length of the wavelength between two crests of a wave at 30 megahertz or 27 megahertz. Light waves, a photon has a frequency of a big ass number. Its wavelength is a little ass number, like this one, 640 nanometers. So they use 10 to the 14 hertz. It's just the numbers get crazy when you get up into the light area. But I wanted to talk a little bit about velocity factor to just kind of throw that in there. And so light doesn't only have a wave, it has.
I think it is legitimate.
Want more Sleep Space episodes?
Let me just go through these.
A candle has no battery.
Of course not. Well,
Let's go back to our electron. Suppose now that I choose space will generate an electric field around about electric field at a given point in.
All right, so before we get into electric fields, before we get into field theory, so you still have particles. You think, well, there's no particles coming off the magnet. Well, there's charges, and the charges interfere with each other, and they make that interference makes the fields. I don't know if we look at this one here.
The following content is provided.
If we just zoom ahead here, I don't know where that picture was. He had a good picture there that explained. Okay, right here. So this is a nature of light. It's not the entire picture though, because there's something else. I'm going to get into that. So they say that light is an electromagnetic wave, and if you have like the old TVs and the oscilloscopes that we have, they use electromagnetic fields to very high voltages to control the field so that you can see what the frequencies look like when you put it into the scope. It changes the electricity to a light wave, and the coils and stuff inside of the cathode ray tube are such that the voltages change the light wave that's inside the cathode ray tube to show you what the wave looks like. Pretty cool thing. So what we've got here are two waves. One wave goes up and down, and the other wave goes across. So X is your, well, actually this axis is wrong, okay? Here we have this beautiful, this is coming from MIT. What the fuck? This is wrong, okay? This fucking axis is wrong. Oh my god, it's so wrong. I'm gonna have to, I gotta bring up paint. Oh my god in heaven. Alright, let's open up this with paint right here. I'm gonna prove something to you, that these professors don't know everything that you think they know. Oh, you don't know what you're talking about. Yeah, the hell I don't. I'm gonna prove it to you right now. So we're gonna start a new thing here, and we'll just convert this to black. We're gonna draw an axis. We'll use I'll probably use this thick line, and we've been using, use the red axis, and we'll go here. We're gonna draw an axis. All right, so the first axis, actually, let's draw a gray line, and we're gonna draw. Let's go. Let's go right here. Now, in normal classical mathematics, you would call this the x-axis, okay? But really, in fact, it's not, okay? This axis right here, and we're going to write this down. This axis is called, and it's not even in the right frickin' size here. This is the t-axis. This means time, okay? So, so you have time, and now let's see if I get the right size. All right, so this is going to be, whoops, we'll do a line, and we'll just do a line from here. And we'll do a line from here. And we will call this, the x. This is the x-axis. Now we'll do another set of lines. Oh, no, that's incorrect. That's incorrect. I stand corrected here. Let's even go a little bit further here. Let's go ahead and black this out. Let's choose yellow and line and 2. Okay, so we're gonna go here. It's a little bit off. I should bring this up a bit higher. Let me go to our pen. So this axis is called the y-axis because it's up and down. Now, or is it the x-axis? I don't no. This might be the x-axis, and the y-axis is... Oh, shit, I don't know. Am I wrong? Would that be the x? No, it's the y-axis, okay? So the x-axis we'll do in red. Oh shit. I didn't use my straight line. This is called the x. So when you think in terms of time, a light wave travels through space. It just doesn't sit in one place, okay? It's a time variable. So it has a wavelength, but there's two things going on here. Light has two components. It has a magnetic component and an electric component, okay? Now, depending on how you look at it in that picture, let me just go back real quick and we'll look at the picture. So the electrical component he has going up and down. That's the vector E. The vector B is the magnetic component, okay? So I don't know if, let me go back and look at it again and see if he has, see he's got vector E over delta T. The magnetic component is 1 over the speed of light, whatever the hell that is. I don't know what he's doing there. And K is on a vector Z, which doesn't really... He's showing the X as being up and down and the Y being across. That's really not true either. That his fucking curve is all backwards, okay? In a normal... I gotta do this to explain this to you people. Alright, so let's grab over here. Let's go over here. On the lower corner, this is a separate graph, okay? And we'll just use the same, we'll use a different color. Like so. This is X. Okay, so this is red. So, alright, so normally you have this graph. In regular mathematics, when you're doing equations, your x-axis is horizontal, your y-axis is vertical, okay? This is proof why this MIT professor got his fucking curves all fucking backwards. What the hell is wrong with these people? They're confusing students. I mean, God almighty in heaven. I'm telling you, I want to have a conniption fit over these effing YouTube videos teaching this information. There's so much misinformation out there. Fuck. Alright, so what happens is, so we draw another graph here. And now the graph, the line, we're going to draw only one line, okay? The line is going to be in this direction here. And what I'm going to do, I'll put some arrows in here so that it will be, this is also T, right here. This is T. This is time. So you've got this yellow, you've got this XY axis, and it's moving forward in time, okay? That's why the X looks weird. In a classical mathematical formula, when you have a box, and the box looks like this. Sorry for my, I'm doing a perspective drawing here. So when you look at the box, you have an axis, all right? So you've got yellow, which is y, here, and you've got x, which is here, and you've got another color which goes out into, it goes into the board, into the thing. So what you have here is you have a three-dimensional picture projected on a two-dimensional plane, okay? And so that's your x and y, and now instead of t, you have z, okay? So you have a z-axis. That's a three-dimensional object. Now, we know for a fact that a photon or an electron is a three-dimensional object. It's a little sphere. Well, we're not representing the particle. We're representing the wave. So you've got this little dot, and the dot is an infinitesimally small dot, and it goes around in circles and up and down and every other which way but loose. But it goes forward into time. It never goes backwards. It always goes forward. So that's why my interpretation is the best, and it's the correct interpretation of the EM wave of light. Okay, so getting back. So now we have yellow, and I'll use a slightly lighter line. The yellow is the up and down, and so you've got your line like this, and so on and so forth. Okay, and he showed some lines through it and stuff. I don't really want to put the lines in. So then on the x-axis, we'll change the color a little bit along the same idea. You've got, this is like, it's like flattened out, you know what I'm saying? The y curve is up and down. The x curve is flat against the plane. It's on that plane. Now so the other thing, we have what's called polarization. So here's the problem. Okay, I'm going to say that this is the magnetic wave. I'm going to use the letter M instead of B, and this is the electric wave. Oh shit. This is the electric wave, okay? And we call this an EM wave because it has bits and pieces of both, okay? So there's a thing called a polarizer, and theoretically we can take a polarizer, and I will just we could just do like one circle. No, wait. Yeah, we do one big circle here. And so the circle encompasses both the EM wave. It's the EM wave is within this circle. Now, you have what's called, we'll do it with this color. You've got horizontal polarization. Which is the red. And then you've got vertical polarization. Which is the yellow. So if you use vertical polarization, it allows only, I may have this backwards, it allows only the yellow vertical waves to go through and not the red waves, okay? If you use horizontal polarization, which is like this, then you only get, it's hard to tell, but you get the XY, you only get the X plane. As it turns out, there is another form of polarization, and it is called circular. If I try to draw a spiral, oh shit, I did it wrong. Let me, because you've got to draw this spiral in terms of time. And so I kind of screwed that up a little. Let me try it again here. So, I don't know, like, how they, yeah, I don't know. Maybe it just goes like this. I don't know. It's actually forward in time, so the loops don't actually cross over. Because it's forward in time. This is called circular polarization. So you've got to have, it's called a helical wave, and you would have to have a helical type of filter in there to see if there's any, any circular. So you could use a vertical and a horizontal, but that would effectively shut off everything. Depending on the antenna, if you have an antenna that looks like that coil up there, that will put out circular polarization. If you have an antenna that is only on the X plane, it'll put out horizontal polarization, like a dipole. It's called a dipole. If you have an antenna that looks like the Y, that's called a vertical antenna. It will put out your electric waves. That's actually a good question too. Damn it. Let me go to here. I know that a vertical antenna puts out vertical polarization, but I don't know. Yeah, that would be Y. Is a vertical antenna vertically polarized? Oh, fuck, I don't want fucking AI. Go get the fuck out of there. Yes, a vertical antenna is vertically polarized. Its physical orientation dictates that the electrical E-plane field of the radiated wave is perpendicular to the Earth's surface. And they show you a picture here. So you can see the electric field being on the y-axis and the horizontal field is on the x-axis. I don't even know if they show that, but anyway. So getting back to my lovely graph, you can use a polarizer. You can eliminate one of the fields, and depending on, and you can rotate this polarizer to, you might have the strongest field might be in the middle. It might be at 45 degrees. But what happens to the wave when you use this polarizer? Does a polarizer eliminate magnetic waves? So let's ask this question here. I really hate that garbage coming up. Let's go ahead and do it here. A polarizer does not eliminate the magnetic component of an electromagnetic wave. Okay, I was pretty sure that this was true. Electromagnetic wave, like visible light, is a coupled wave made of both an electric field and a magnetic field. These two fields exist together and continuously feed into each other as the wave travels. You cannot completely remove one without destroying the wave itself. It only filters the electric field. Polarizer filters waves by restricting the oscillation of the electric field to one specific direction. It does this by absorbing the components of the electric field that do not align with its molecular axis. The magnetic field remains intact because the magnetic field is always perpendicular. You cannot have one without the other. You can't have one without the other. Love and marriage go together like a horse and carriage. Do-do-do-do-do-do. You can't have one without the other. Slide in there. You cannot have one without the other. The surviving polarized wave will still carry a magnetic field, but it is locked to the direction of the newly polarized electric field. I can provide information on materials designed for magnetic shielding, Faraday cages and such. How do polarizing affect field? Unpolarized light has all kinds of waves in different directions. Each of these waves has its own electric and magnetic fields, which are perpendicular to each other. A filter, the electromagnetic wave that results is polarized only in one direction. There still exists both an electric and magnetic field to this wave. The graphic below illustrates this fact and shows only the electric field. In reality, there is still a magnetic field that oscillates perpendicular to the polarizing field. Vertically polarized light wave. About 50% income is equally distributed. The polarizer rotate the M waves parallel to the slits. Just by placing a third polarizer without this polarizer light doesn't go through 5 degrees. In waves you can see the light polarizer. This amazing fact shows the slit's influence of EM waves. So there's the magnetic field's still there, but it just, I don't know what it does really. So it says the magnetic field is still there, but it's weak, you know. I don't know. Yeah. Okay, continuing on. So I don't have this information here up here. Okay, so let's go ahead and look this up. I really don't want to see this garbage. I'll just get a dark page here. I'll do it right here. So what we're going to look at is SAM and OAM photons. And what this is that they've determined that as the photon travels through space, the photon itself has some attributes. Photons can carry two distinct types of angular momentum: spin angular momentum and orbital angular momentum. Both are properties of light, etc., etc., etc. SAM is associated with the polarization of light. So when we're affecting a spin angular momentum by electrically polarizing the electric wave. It determines whether the electric field of the light wave oscillates linearly, elliptically, or circularly. And they've determined, it says each individual photon carries a spin angular momentum of plus or minus h, where h is the reduced Planck constant. They've actually determined, and they say it's a whole number, but they actually determined that there's a half spin or something, and it uses half of the value of that constant. Intrinsic rotation of the M field, let's help you out. Okay, now we got the orbital. It's a spatial structure. Instead of a flat wavefront, the light twists around the axis of propagation, which is that t-axis. So it goes around, and it creates this donut. So light actually creates a donut hole in the middle. It's twisting around. This is the momentum of the photons as it goes through, creating a donut-shaped intensity profile with a dark spot in the center of the orbital vortex. Unlike SAM, it is strictly limited to plus minus 1, but OEM can have infinite unbounded values, allowing it to encode much more data into a single photon. That tells you a lot right there. It tells you I know what the frick I'm talking about information and photons. It talks about some other stuff in there. Oh. So, whether or not this information... Okay, I'm really actually more particularly interested in the magnetic information, because the information that I'm looking for, I think, is more of a magnetic nature. So maybe we're looking for, or I could be wrong, you know, it could be electrical, but I have not done any work with static electricity. I started to do some stuff with static electricity and high voltage and that sort of thing to come up with some noise stuff, and I haven't been able to do it. In this particular project, we are going to be amplifying low light waves using FETs anyway, so we might be able to incorporate a fairly high voltage static electric field and use that as, could even use it as a source of noise and stick it in the enclosure. It's all full of metal, so it will, you know, keep that energy in there, but we'd have to have I don't know how to, like, have a high voltage in there, but have a really small, like a bead for an antenna or something, you know, and have a way to measure that electrostatic field and see what it does. On-chip generators, you know, they were talking about this to make these micro rings and having the light travel through the micro ring and actually slow down the speed of light. That's sort of what I was getting into earlier, but I never got there. Let's go ahead and see what's up with these videos. What the hell, right?
So much stranger than you might think. Sure, it may seem simple enough, traveling around the universe, delivering energy from one place to another. It helps us see. It provides life to plants, and thus to our planet generally. It has a reputation for being very fast. And yet, for a source of energy that has become synonymous with greater understanding, light is surprisingly difficult to understand. Light helps us see other things better, sure, but when scientists tried to look at light itself, it was surprisingly difficult. No, I don't mean that they started staring into any lamps. Please don't do that at home. But experiments in the last 200 years or so have proven that what light appears to be and what light is, a strange striped pattern next to each other will start to both constructively and destructively interfere with each other. It used to be because electrons in the metal were getting knocked off it by the increased energy the light was imparting. Imagine it like a fruit on a tree. If you pull the fruit off the tree, you need to use a certain amount of energy. Once the energy is greater than the strength of the it was a bit of a puzzler. Albert Einstein was the man who solved the puzzle. He deduced that light must be traveling in little packets of energy, so sending more of them, increasing the frequency, was the only way to increase the energy going to the electrons. He called these packets photons and later earned a Nobel Prize for his work.
So yeah, there's group velocity and there's singular velocity. And they're saying that they can slow down the speed of light using group velocity as the packets of information. And I don't think that's analogous to packet communications. But you tell me.
Light, it seemed, was more like a particle again. Or both a wave and a particle at once? Of course, somehow, the single photon, which was leaving the detector like a particle and was arriving at its destination as a particle, if you ran the experiment multiple times, you could quantify those probabilities, discovering that it would be black. But add a third lens and place it at a 45-degree angle between the other two, and bizarrely, light starts making it through all three lenses again. This may seem counterintuitive. How does adding more blockages increase the amount of light that makes it through? But this result actually rules out the possibility that the light has a fixed orientation. It must be snapping into focus at each new lens, rolling a quantum dice each time to see if it was the right orientation all along or not. If it makes it through the first lens, a 50% chance, it only did so because it was oriented perfectly perpendicular to the lens's polarization, which means once it reaches the second, it's coming at it from a polarization that's diagonal. So once again, there's a 50-50 chance that it makes it through. It rolls a quantum dice again, and once again has a 50-50 chance of proceeding. If it gets through this hurdle too, then it again snaps to the new orientation, as if it were
Next.
To make the argument that given what we know about the universe, that kind of length, and that's what we did. Is there some unit of measurement that we could all agree on? The strength of gravity, the speed of light, and Planck's constant. So it would seem that it should have something to do with the deep structure of the universe. And indeed, it does. How important is it? Well, let me give you some examples of the Planck area surrounding that region, 1970s. It turns out that the entropy of a black hole, which is the amount of information hidden within it, is equal to the surface area of the event horizon of the black hole in square Planck lengths. That's an astonishing result. But just think about that for a moment. It's telling us that the amount of information stored in a region of space, in this case, a black hole, is equal to the surface area surrounding that region in square Planck lengths. That's a bizarre result. So it does seem that the Planck length is fundamentally important. And here's another property of the Planck length. So let's say we want to make an observation of some very small thing. So how do you observe something that's very small? Well, one way to do it is shine a light on it to see where it is, right? To get it, that's the way that we observe things with our eyes. So you might say, well, it's tiny, so I have to shine light with a very small wavelength onto this thing to see the tiny thing. The wavelength can't be bigger than the tiny thing, otherwise you won't see it. So the smaller this thing is, the smaller the wavelength of the light that I've got to shine on it. But remember, quantum mechanics tells us that the smaller the wavelength of the light, the higher the energy of the photons. So I have to start bombarding this thing with higher energy photons to see it. What happens if you try to approach something that's the Planck length? You get so much energy in there that what you do is you form a black hole. And then you put more energy in, you try to see what's going on, and the black hole grows. And so you get to a point, which is around the Planck length in size, where you can't, in principle, try to resolve the structure of this thing. It starts to go bigger again, because you make a bigger and bigger black hole.
check the pin comment or stay only speed light can travel at, and interestingly, seems to stick to that number regardless of your frame of reference. Two people could be traveling through space, one at 1% the field that in turn creates a magnetic field, A second light wave is created by these moving particles that crucially overlaps the waves of the original light, albeit one that waves at a slightly different pace to the original light. Exactly what speed varies depending on the material. When two waves meet, they interfere with each other. They take an average, sometimes interfering constructively to build each other up, and sometimes working against each other. So when you take the grand total of all the ups and downs of each wave, you actually end up with a new wave, one that travels at a different speed to the other two, and one that goes slower than the speed of light. Eventually, this propagating wave can reach the edge of the blocking material, and without those electrons interfering anymore, you're left with just the original light again, which is then free to travel along its original path again, at its original speed, as if nothing had ever happened. Scientists have had a lot of fun with this concept over the years. Researcher Lene Howe at Harvard in 1999 was able to slow down light to an astonishing 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to 1/1000th of a degree above absolute zero. 2 years later, Howe managed to slow down light speed to 0 before warming up the cloud and sending it on its way again. You might find that result surprising. However, strange things have happened in the opposite direction too. In 2000, researchers at the NEC Research Institute in Princeton, New Jersey, sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed that it exited before it had entered. While this might appear to mess with causality, how can you leave a building before you go inside it after all? Fortunately, there was a simple explanation that saved us from creating too many paradoxes.
Going around the edge.
Although the light pulse traveled faster than light, the light itself did not. This was more an optical illusion than a refutation of Einstein's relativity. Let's take a closer look at a photon of light. Each photon represents a tiny packet of waves, moving up and down. The speed the waves inside the packet propagate is known as its phase velocity, while the speed at which the packet as a whole is traveling is known as the group velocity. You can also have a wavefront
That's what I
velocity,
just learned
which is
today.
how fast the first photon in a wave of photons can travel. This is a little heavy in its terminology, so let's explain it with an example. Think of a crowd of people doing a Mexican wave. The wave that the people are doing is the phase velocity. You can see the wave traveling along through the crowd. It might look like it's traveling quickly, but the crowd itself isn't going anywhere, so our wave's true speed is 0. These people are the group velocity, or possibly the wavefront velocity. Let's imagine that we wanted to send our crowd marching. They could do so and could
That's
keep
good.
doing a Mexican wave as they traveled. But although their waving hands might make the wave go really fast in the direction of their travel, it would vanish whenever it reached the front of the crowd. Information exchange couldn't go faster than the walking speed of the crowd itself, regardless of how fast the peaks in the wave seemed to be traveling. Einstein in relativity never claimed that phase velocity couldn't exceed light speed. He just claimed that information couldn't travel faster than light. And if you're trying to deliver a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast they're waving. Until the first person in the crowd arrives, no information can be delivered. Still, this difference between the waves within light and the speed of light itself will become interesting in our next experiment. And this is where things start to get a little weird. Oh, you thought it was weird already? Oh no, this is the really physics-defying part.
Good
Let's
stuff.
go back to an experiment we've looked at before, the double slit experiment. I go into more depth on this experiment in my video here. If you haven't watched it already, I really recommend you do so, as I'm going to assume you know what this experiment is for the part that comes next. This experiment is a fascinating exploration of how light can sometimes behave like a wave and sometimes like a particle. However, In 2023, researchers from the Imperial College figured out a way to separate the slits of this experiment, not in space, but in time. The way they did this was simple. They took a transparent material called indium tin oxide that, under specific conditions, can be made to be reflective. Indium tin oxide is the stuff they use in most mobile phone screens. They fired a laser at it, and then rapidly changed the material from transparent to reflective and then back again. This left only a slim window, a few femtoseconds, where the laser was reflected. They called this a time slit. They recorded what the laser looked like after it had been reflected, and found that its frequency had spread out a little bit in the process, but other than that, nothing too crazy had happened. The weird thing was what happened when they sent 2 laser pulses through these time slits in rapid succession. The position of the emitter, the mirror, and the receiver remained the same. The only thing different was the time the lasers went through. Oddly enough, when 2 went through, an interference pattern happened. This was not an interference pattern in the same sense as with the regular 3D space double slit experiment though. This was an interference pattern that had affected the laser's frequency. Certain frequencies of light within the laser faded out, exactly in line with the way intensity faded out in the regular version of the double slit experiment. To visualize why this might be happening, let's draw out this experiment in regards to time.
Saying the frequency changed.
The time slit experiment can be drawn in a similar way to the double slit experiment, except we are going to need to visualize the change in the experiment over time. To do that, let's create a 4D graph where space is along the x-axis and time is along the y-axis. This is easy enough to do. It just looks like this. The photon leaves the emitter to the left, hits the time slit, is reflected, and arrives at the receiver. I've drawn this as a continuous line just to make things simpler later, but the idea works just as well either way. Later, a second photon is released from the emitter. It reflects and arrives at the receiver at a slightly later time, represented in how it takes place higher up, further into the future on our time graph. If light behaved normally, traveling along at the speed it was supposed to go at, this would be the end of it. Instead, light is interfering with itself. This means it must be traveling along a path that takes it through the other slit as well as its own. This is the only way that light could come in with the pattern that we see. And just like in the double slit experiment, it's likely happening on the other side of the slits too.
He's using 2 separate
As for why
beams.
it's frequency and not intensity that's being messed with here, think about the implications of what you might see if light did indeed come in at a different angle like this. Photons come in little packets of waves, as I've previously mentioned. Now look at what happens if you change the angle at which those waves arrive. Here's how it normally might look.
That's a longer frequency.
I've added a black timeline here and have highlighted every time the receiver receives a new peak in the wave.
Yeah.
Here's what
I get
happens when you alter the direction of the wave's arrival. Suddenly, the peaks are coming in much more frequently. The frequency of a wave over time is very much connected to the color we perceive light to be.
When they come in
Lower
at an
frequency
angle, they're
light
coming
is
in
redder
more
in color.
frequently.
Increasing the frequency shifts light's color towards blue. So this color variation makes sense. What makes less sense is what's going on with the paths this light is taking through time. Remember, the straight lines we started
That's
with
longer.
represent the 299,792,458 meters per second
That's a
that we
longer
see light traveling.
traveling distance.
So what can we say about the photons that are traveling along
is it?
these paths?
No, it's not.
For some parts of their journey, they are traveling slower than the speed of light, taking more time to arrive at a destination that's the same distance away. And yet, for other parts of their journey, they are traveling faster than causality ought to allow. From their perspective, they are traveling backwards in time. As a reminder, these 2 emitters on the left are actually the same one, just at different points in time. The same for the receivers on the right. It
is a mind-bending result.
It's the
And yet,
same.
according to the results of this experiment performed by a research team at the Imperial College in London, this is what is occurring. The implications of this are startling. Light always travels the path of least time, the route that allows it to arrive at its destination along the path closest to
Okay, so this is freaking new here.
299,792,458 meters per
Instead of having a continual light beam, they're saying that they pulsed the light, but they did it in a period of femtoseconds. That's like taking a shutter. That's like a super high-speed camera to turn that light on and off. I don't have the ability to do that. So they're saying that's one way of changing the frequency, or I mean, my theory is that that's fine, but I think it's just better to change the phase. I'm doing something at a level that's, I'm not going to say sandbox. I'll say it's a level at high school level compared to PhD level, because I don't have the resources to create femtosecond pulses of light in order to see a frequency change in the light versus the intensity change. However, I am looking for frequency changes in light, but I've come up with a different plan to do it, and I'm able to do it, but anyway.
second, the fastest anything in the universe apparently can go. And yet, it seems that in its efforts to locate exactly what path that might involve, light is testing the waters, putting out feelers that check to see if other paths, and seemingly other paths through time itself, might present a more viable solution. These feelers are interfering with photons that travel alongside it, but also with photons that travel a little ahead or behind it in time. To be clear, we never actually detect photons taking any of these other paths. We don't see photons coming in from the future. We never see photons traveling slower than the speed of light, provided there is no supercooling gases providing an explanation for why they slow down. And yet, for interference patterns to occur, to at least some extent, light must be trying out alternative routes through time. Perhaps it's like lightning, testing.
So who's this guy? That was a pretty good little video. I'm gonna go ahead and, I don't know exactly who this dude is, but I will just put him kind of down at the bottom somewhere. He's got some interesting videos. Pulses, yeah, but you know, I don't have the ability to mess with that.
No wire and no circuit, just wax, a wick, and fire. And yet, physics says that the light coming from this candle is an electromagnetic wave, not just candlelight. Every type of light we see is basically an electromagnetic wave. That means hidden inside this simple flame, there is a story of electric fields and magnetic fields. But where are these electric and magnetic fields hiding inside a simple candle flame? And when we say that light is an electromagnetic wave, what do we really mean? In this video, I will tell you exactly why light fields
check the
hiding
graph
in
out.
not just candle.
Check the graph. Okay, so he's got the x-axis on the time, which is wrong. He's got the y-axis correct. And the z-axis is supposed to be the x-axis, and x is supposed to be t.
Light. Every type of light we see is basically an electromagnetic wave. That means hidden inside this simple flame, there is a story of electric fields and magnetic fields. But where are these electric and magnetic fields hiding inside a simple candle flame? And when we say that light is an electromagnetic wave, What do we really mean? In this video, I will tell you exactly why light is called electromagnetic radiation and what the electromagnetic spectrum really means in the simplest way possible.
Yeah, we'll see about that.
Saying this specifically because there are situations where a magnetic field can exist even without an actual magnet. We will see that soon. Now let us move to electric fields. When we were in school, we used to take a plastic scale, rub it on our hair, and then bring it near small pieces of paper. The paper pieces would jump toward the scale. This is not magnetism. A magnet mainly attracts materials like iron, but here, paper is getting attracted. What is acting here is an electric field. When we rub the plastic scale on hair, some
changing
loose
the
electrons
charges.
move from the hair to the scale. Because of that, the scale becomes electrically charged. This is what we call static electricity. Once the scale is charged, it creates an invisible electric field around it. When small paper pieces come into this field, they are attracted toward the scale. So just like a magnet creates a magnetic field around it, an electric charge creates an electric field around it. Electric fields are usually represented using field lines. These field lines also have directions. In simple diagrams, electric field lines are shown as going away from positive charges and toward negative charges. The detailed direction is not very important for us now. What we need to remember is this. Just like in the case of magnets, even though the electric field is caused by charges, the field itself is not a part of the charge. It exists in the surrounding space. And there are instances where an electric field can be created even without a charge sitting there as its direct source. Now that we have the basic idea of both electric and magnetic fields, let us dive into a bit of history. For a long time, electricity and magnetism were treated as two separate things. But in 1820, a scientist named Ampere showed a surprising connection. A moving electric charge can create a magnetic field. For example, this is a conductor. Both ends of this conductor are connected to a battery so that an electric current flows through it. Current is nothing but moving charges. In such a situation, these moving charges create a magnetic field.
Okay, stop right here. Let me think about this for a minute. It depends on the direction. If the direction's going down, that's showing a counterclockwise movement. We learned about this with the fingers and stuff. If the charge goes up, so depending on the direction of the moving charge through the wire, it changes the orientation of the magnetic field. If we go back and look at the light diagram, and let me just bring up my, is that it? No. If we bring up this diagram, the magnetic field is on the x-axis. So if we were to run the wire, well, the wire just goes straight through anyway. It's going to be a circular polarization. If I use a wire, it's a circular polarization. If I use a magnetic field, I can use the plane because then only a very small portion of the magnetic field is going to be interfered with. Maybe it's better to, I'm trying to figure out what the idea would be to not control, but affect the magnetic field in a light wave. And it's on a planar, it's on a plane. Whereas this shows circular. But if you go back to that video, he's got both of those fields on a plane, and it's flying away to Spain.
Around the conductor. and the direction of
Like
that
back
field
here.
will be in concentric circles around the conductor.
Yeah.
Diagramming space, things. But in 1820, we have the basic idea of
So here we've got fields. Fields are created by either electricity or magnetism, or a magnet, let's say. The magnetic field is the one I'm interested in. The magnetic field is on a plane, and it is moving forward. If you rotated that magnet maybe 45 degrees across underneath that light. So I've got some magnets, but you'd have to have like really high powered magnets and stuff to mess with that probably.
the reverse effect. If a magnetic field near a conductor is changing, it can create voltage in that conductor. For example, if we move a magnet near a copper coil, the magnetic field passing through the coil keeps changing. Because of that changing magnetic field, a voltage is induced in the coil, and if the circuit is closed, current can flow. So now we have the second important point. A changing magnetic field can create an electric field, and that electric field can drive current in a conductor. Then came James Clerk Maxwell in the 1860s. Maxwell studied all these earlier discoveries and combined them into a deeper theory of electricity and magnetism. Ampere had shown that moving electric charges can create a magnetic field. Faraday had shown that a changing magnetic field can create an electric field. Maxwell looked at these two ideas together and asked a deeper question. If electricity can create magnetism and magnetism can create electricity, can they keep creating each other? In other words, can a changing electric field create a changing magnetic field? And can that changing magnetic field again create a changing electric field? Maxwell realized that this is possible. Now imagine a current flowing through a conductor. That current creates a magnetic field around the conductor. But if the current is alternating, the current is not steady. It is continuously changing direction. So the magnetic field around the conductor will also keep changing. This changing magnetic field can create a changing electric field, and that changing electric field can again create a changing magnetic field. In this way, the electric field and magnetic field can keep creating each other and move forward through space. If we want to see a similar idea in a mechanical system, we can look at a pendulum. When we pull a pendulum to one side and release it, we give it energy. At the highest point, that energy is mainly stored as potential energy. When the pendulum moves down, that potential energy becomes kinetic energy. At the lowest point, the pendulum has maximum speed. Because of that kinetic energy, it does not stop there. It moves to the other side, and the kinetic energy again becomes potential energy. Then the static field creates a changing electric field, and that changing electric field again creates a changing magnetic field. Once this linked field pattern is formed, it can continue moving through space. When those waves travel far away and reach another antenna, they can make electrons in that receiving antenna move. That movement creates a small alternating current in the already known values of μ0 and epsilon0 in this formula. He got a value of approximately 300,000 kilometers per second. But 300,000 kilometers per second is the speed of light. This speed had already been measured through clever experiments, which I have explained in one of my previous videos. So Maxwell realized something extraordinary. The speed of electromagnetic waves, derived from the basic laws of electricity and magnetism, was matching the measured speed of light. That was the moment he understood that light itself is an electromagnetic wave. Today we know that electromagnetic radiation is not just one thing. It is a whole family of radiations. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all electromagnetic waves. Together, this complete family is called the electromagnetic spectrum. The main difference between these waves is their wavelength and frequency. Wavelength means the distance between two consecutive peaks of the wave. Frequency means how many wave cycles pass through a point in 1 second. In the antenna example we discussed earlier, the frequency of the electromagnetic wave produced by the antenna will be the same as the frequency of the alternating current supplied to that antenna.
Now, in order for this to be at maximum, the antenna is cut to a length that resonates at the same frequency of the receiving wave. So that's called you've got a half-wave dipole. And so a half-wave dipole, it takes half of the wave on one side, the other half on the other side, and it creates a standing wave. That's like the cavity thing that we were talking about a little bit earlier, whereas you're taking multiples of the harmonics and you're adding all of that stuff together in that cavity, because the wavelength of light is so small that you've got to do numerous amounts of those wavelengths in order to get it to work. Here, you're doing it the length, because of the frequencies. As you get higher and higher, the wavelengths get smaller. It's easier to make. The distance, there's a formula for the distance, the length of the antenna, which is 468 over the frequency in megahertz, something like that. So there's a change according to that formula, and I don't know exactly the relationship between the length of the antenna and the length of the standing wave that goes into the antenna. It's like it's a different number.
That means if the current in the antenna is changing thousands of times per second, the electromagnetic wave produced by it will also have thousands of cycles per second. If the frequency is low, the wavelength will be long. If the frequency is high, the wavelength will be short. Radio waves have the lowest frequency and the longest wavelength in this group. After radio waves come microwaves, then infrared, then visible light. Visible light is only the small part of the electromagnetic spectrum that our eyes can detect. Within visible light itself, different colors have different wavelengths and frequencies. Beyond visible light comes ultraviolet, then X-rays, and finally gamma rays of the alternating current supplied to the antenna. So a natural question comes here. If visible light is also an electromagnetic wave, can we produce visible light from an antenna in the same way? Can we send an alternating current with the frequency of visible light through an antenna and produce light? Theoretically, the idea is not wrong, but practically it is extremely difficult. The first problem is frequency. The frequency of visible light is more than 400 terahertz. That means the current has to oscillate more than 400 trillion times in 1 second.
Yeah, that's
We
pretty
cannot
fast.
create such an extremely high frequency current using ordinary electronic circuits and antennas. The second problem is size. The length of radio antennas are usually related to the wavelength of the radio waves they produce. Since radio waves can have long wavelengths, their antennas can also be large. But visible light has wavelengths in nanometers. That is an extremely tiny scale. So, using an ordinary antenna and alternating current, we cannot practically produce visible light in the way we produce radio waves. But that does not mean visible light is not electromagnetic radiation. An antenna is not the only way to produce electromagnetic waves. For example, take an ordinary incandescent bulb. Inside it, there is a tungsten filament. When electric current passes through this filament, it becomes extremely hot and starts glowing. When any object becomes very hot, the atoms inside it vibrate more violently. Heat is basically connected to the random motion and vibration of particles. In a hot tungsten filament, the atoms and electrons are moving and vibrating at extremely high rates. Since electrons are charged particles, their motion can produce electromagnetic radiation. Some of that radiation falls in the visible range of the electromagnetic spectrum. That is the light we see from the bulb. Now coming back to the candle flame. A candle flame has no battery, no wire, and no antenna. But inside the flame, wax vapor is burning and releasing heat. The burning flame contains tiny soot particles, various types of molecules, atoms, and ions. The flame heats up these particles and makes them vibrate. Inside those hot particles, charged particles are moving and vibrating. Because of this motion of charges, electromagnetic radiation is produced. some of that radiation falls in the visible range of the spectrum. That is the candlelight we see. Waves as particles called photons, but quantum mechanics did not say that light is not electromagnetic radiation. So I hope you have now understood what electromagnetic radiation is, what the electromagnetic spectrum means.
Space will generate an electric field around it of alternative current. The electron will move back and forth for cosine or sine curve. In the second part, does the electric field it generates as well as the induced refer as an electromagnetic wave or EM wave. Quadrillion of Hertz. Quadrillion of Hertz. Increase the frequency a little more, up to 1 quadrillion of Hertz. The metallic bar starts to glow now. It emits visible light. Did you enjoy this video? Then like, subscribe and hit
to the x direction, and the other one is actually pointing to the y direction, which is the B field. Okay, and those lines doesn't mean a lot because those are actually just connecting the endpoint of all those vectors, right? So you can see that there are sine wave structure or cosine wave structure. Okay, K vector is actually giving you information about the wave number and also the direction of propagation. Okay, and in this case, what I'm trying to construct is a solution which is actually propagating along in the direction of the K vector, and the electric field is actually going to be pointing to a direction perpendicular to the direction of the K vector. Okay, so basically what I can do is I can write this Planck wave in this functional form. E0 is actually a vector, which is actually telling you the direction of the electric field. Okay, that you can actually apply this the technique which we learned here. So what can I do to cancel the electric field? This is actually very similar to the situation when you have a progressing wave on the string hitting a wall, right? Because the magnitude of the string, okay, with respect to the equilibrium position is actually equal to 0, okay? That's actually what we have learned in the last few lectures. And
I'm going to bust your ass so damn quick, it's going to make your head spin. Goodbye. I don't know why Nightbot's not eliminating this stream boost shit. It's really pissing me off.
And this is actually exactly the same situation, right? You have a progressing wave, and there is some kind of boundary, which actually when this progressing Planck wave encounter this perfect conductor, there the electric field, the boundary condition, has to be E is actually 0, 0, 0. EXY 0, which is actually the position of the Z of the perfect conductor, as a function of time, will be equal to 0. Okay, the whole plane will have 0 electric field. Okay, so that means there must be what kind of wave? There must be a refractive wave, right? Because of the presence of the perfect conductor, right? It's actually similar to the situation which we discussed. There's a progressing wave hitting the wall, and on this string wall system, there will be a refractive wave coming out of it. Okay, so therefore, what we are expecting,
getting into the math of refraction and shit like
and vary in turn through this mutual disturbance process.
that.
The movement that has been imposed This is what is used for microwave ovens, telecommunications, and other remote glowing, but we can detect them with thermal imaging to be non-polarized. Polarization. As we have seen previously, electron clouds in atoms behave as if they were connected to the nucleus by a rubber band. When atoms are agitated, electron clouds vibrate around nuclei in all directions, and the waves that are generated have a very chaotic shape. This type of wave is said to be non-polarized. Imagine sending a wave of this shape onto a charged particle. The particle will undergo a force because it interacts with the electric and magnetic fields that make up the wave. It will start to vibrate like the wave, and therefore like the atoms which produced it. It is in this way, for instance, that the sun can warm the Earth's atmosphere despite being millions of kilometers away. Its heat is transmitted from its surface via electromagnetic waves through the vacuum of space. However, it is possible to make atoms vibrate in a much more controlled way. The electron clouds can vibrate in one of three possible ways. Let's imagine a marble placed on a table and which is connected to a nail using a very tight rubber band. Let's imagine now that we launch the marble. We observe that its trajectory will most often form ellipses and sometimes either straight lines or perfect circles. Within atoms, electron clouds are attracted to the nucleus in the same way that the marble is attracted to the nail. Thus, they will also vibrate in one of these three possible ways, and generate very clean electromagnetic waves, which are said to be polarized, with either rectilinear, elliptical, or circular polarization. Radio antennas, for instance, cause atoms to oscillate along the axis of the antenna. They thus generate very clean waves with a rectilinear polarization. The polarization of light is not directly visible to the naked eye. Our eyes are only sensitive to light intensity, but not to the direction of the fields. Nonetheless, this is a crucial property which influences how light interacts with objects. In particular, there exist filters that can absorb certain polarizations. These filters are called polarizers. They are used for 3D cinema technology in particular, where it is possible to project two images simultaneously with two different polarizations, and to design glasses with polarizing lenses which will only let one of the two polarizations pass.
It's boring.
Finally, as electromagnetic waves are waves, they evolve in space in accordance to very specific principles. Like all waves, they add on to each other. If we superimpose two crests, we will obtain a crest twice as high, whereas if we superimpose a wave with its exact opposite, the two will cancel out perfectly. This first principle of wave superposition is called interference. Wave interference is notably the cause of diffraction, as the wave is energetic. Atoms. This is what gives the metal its ability to conduct
So now what I've learned is I wanted to do this because I wanted to understand the electromagnetic nature of light, so that when I use the polarizer, what exactly is the polarizer doing? Is it affecting the magnetic wave? So every single light wave has a magnetic component regardless of the polarizer. And Jesus, fuck, I hope I'm not getting... Okay, that's just a bone. I hope I'm not getting carpal tunnel in my my wrist. I've got a pain in my wrist. Oh my God. I had a little accident when I went down in the basement. That that bone is higher. It's been bothering me? But I got the same bone on both sides, though. So if I think it's just swollen. I've been doing some. What's been causing that problem? Because my right hand is this is the left hand. What am I like normally doing with my hand? It's causing that. It's like the bone. It just seems more pronounced. And there's a sore. There's been a sore there for a while. And it looks red. I've been noticing that, but I never really paid much attention to it, you know? And it just seems like it's getting worse and worse. It's so fucked up, you know? I got the same bone on both sides. It's like one of them, I don't think it's broken, but why do I have that pain there? Anyway, what the hell was I talking about? You need to know what the polarizer does. So, in my situation, you know, I'm doing certain experiments with the test object wave, and I want to know, I want to be able to increase certain portions. So, I can see that I can filter out a lot of stuff and just have the electric portion of the waves come through. However, and this is a big ass however, is that all of the tests that they've done with these ghost voices and so on, it seems like it's come through magnetically. It seems like the interaction between the noise and the audio frequencies, everything that my understanding is that they are manipulating the magnetic field. They have an easier, it seems easier for the magnetic field to be manipulated because why is it that all the voices seem to appear on cassette tapes and not on the digital tapes, which is more electrical? So I'm inclined to believe that. So if I use the polarizer and have an electric field, it's, I don't know what it's doing to the magnetic field. It just seems like if it's putting more of the electric field through, less of the magnetic field is coming through. So it seems like I need to use, I was thinking of using some kind of an inductor to let the light go through an inductor and let the inductor try to pick off the magnetic variations. But according to this picture, the magnetic variations are on the X plane, but the nature of the photon goes around in a circular motion, and they've talked about this momentum, and so it's if the light were in one place, it would go around in a circle, but the light travels at a very high rate of speed, so it leaves this helical situation, and it's going to do that both electrically and magnetically at the same time. You can't have one wave without the other. But I don't know. Maybe a strong magnetic field through maybe that's the aspect of the test object, is to incorporate an intense magnetic field around that light beam. But I don't think it's going to do, the presence of the magnet itself is going to reflect off of it, so it would have to be, the magnet would have to be encapsulated in light absorbing material, I found a magnet. Matter of fact, I've got a extremely heavy, big ass magnet that I put someplace. Speakers have magnets. And what I was going to do is electrify the speaker and use that as my transmitter, my transmission coil, and have that transmission coil right next to the light beam, and have another coil of some sort as the receiver. But then, no, the light beam itself would be the receiver. So maybe there's I got to get the interferometer set up and calibrated, and then I can start playing with some of the other interesting stuff that goes in there. But it's like, it's almost like I can turn off all the lights in my room and run this experiment almost right on my desk. And, instead of having 12 inches of mirror, I could do 6 inches of mirror, and then 6 inches towards the camera. Like, I've got enough room to do it, and just do half of it. That's probably what's going to happen, because I need to develop the prototype, and I'm doing it on the actual side of the case itself as I'm looking at it. It's like something's telling me to do this, because it's a lot easier to change things and add things when it's out in the open. Then when I get the information and it shows up and I say, hey, there's something there, then I can put it together in the enclosed space, and I can drop the temperature, and I can, amplify shit. But I need to know where to put what, and I need to know what is doing to what. So polarizers affect the electric wave, but is it gonna make the magnetic wave disappear? I wouldn't think that it would. I just don't know here.
Right. Well,
A potato.
It's nothing to think about when
You've heard of X-rays. You've heard of gamma rays. It's all the same thing.
Right.
It is just different ways of preparing your light. Okay? To use my potato analogy.
And so you're basically 11 years old, and you're making this discovery for yourself.
After I realized about the potatoes, yes.
Okay. Because I was 37.
So I said, my gosh, it's all light. It all travels at the speed of light. And this word light, where you're talking about what the human retina can see, that's very limiting for if you want to talk about the universe. Because, so what's our favorite light colors? Red, orange, yellow, green, blue, violet.
YG-Biv.
Okay, continue there, and you go to the other side of violet, you get ultraviolet. You go beyond violet. That's how it got its name. It's beyond violet, and we abbreviate it UV, but I like fleshing out ultraviolet. Give me all the syllables that it's got. Okay? And this is
Sounds far more harmful.
Look, in fact, it is, because in this direction, we are reducing the wavelength of light that's coming to us. And when you reduce the wavelength of light, more energy is packed into one pulse of that light, and so the energy goes up.
Well, okay.
Okay? So the higher the frequency, it's how many crests go by per second, the higher is the energy of that light. So the red, orange, yellow, green, blue, violet is all sort of pretty harmless. You get into ultraviolet light, it has enough energy to break apart biological molecules.
Uh-oh.
And this will give you sunburn and skin cancer.
Right.
Okay? So I heard a DJ talk about when he just learned that the temperature on Venus was 900 degrees. He said, well, you better bring sunblock 1,000,000 for that. So he's wrong. He's thinking that you're protecting from the heat.
That you can block that.
Right, no, you're not blocking heat.
Right.
The point of the sunblock is to block just the UV.
Just the UV.
Okay, right. So
you still getting dark and crispy no matter what you want to do.
Yeah, you'll get toasted. You're toasted, right.
No matter what.
No matter what. So then you go beyond the ultraviolet, and that's when you get the X-rays.
Right.
X-rays is it is continuous with the ultraviolet. right? We put a line there just because our convenience of words and machines built on it, but ultraviolet smoothly transitions to X-rays.
Interesting.
Okay, and X-rays are bad for you because when you go in the X-ray room, what does the X-ray tech do?
They go to a bomb shelter.
Leave the room. They say, "Are you okay? Are you comfortable?" Yeah, okay. Boom. Door closes.
Exactly.
And they look through a lead glass, and then okay. So X-rays can actually penetrate your skin, unlike ultraviolet, and in doing so, it can actually harm your organs. All right, and so you can get organ failure from it. And organ cancers are triggered by this. Now, it's a continuum of a change of wavelength of light. And then you get to beyond X-rays, you get to gamma rays.
Right.
And by the way, gamma rays just keep getting higher and higher energetic, but we don't have more words for it. All right? It's just the last word we've got. But you could have divided that up even more. We just don't. Okay? Right. And so
you would have thought
gamma rays...
Get omega rays or something like
that.
Yeah. I wonder what superhero would be made from omega rays.
Well, gamma rays are, in the early days, before we fully understood what the sources of energy were, there were alpha particles, beta particles, and gamma particles. Alpha, beta, gamma. And the alpha particle is a helium nucleus, the beta particle is an electron, and the gamma ray is a photon. But they all had energies that we could measure, so we're measuring the energies, not knowing what the thing was that caused it at the time. But that all splits out, so we have, like I said, ultraviolet, X-rays, gamma rays. There you have it. All right. We used to call them black light bulbs. I want an ultraviolet bulb, and you turn it on, and you see it. You say, I can see the ultraviolet. No, you're not. You're seeing the violet.
Right.
Okay, there's a little bit of violet spilling out. The actual ultraviolet, you don't see at all. Same with the infrared lamps. You buy an infrared lamp. If that was pure infrared, you turn it on, you wouldn't see a damn thing. Okay?
Right. You're not a predator.
Exactly. So a little bit spills into the red part, so you see the red emitted by the infrared lamp. All right? We can detect infrared not by our eyes, but by our skin. You detect infrared as warmth.
Right.
All right? It's a detector. And then when you get into the meter zone, yards and things, those are inside the television. And there's that secondary knob that you could tune it a little sharper. I don't know if you knew that. Okay? That got you honed in on that one frequency. Was it channel 7, channel 8? Right. We just numbered them. We didn't give you the frequency because that's why, when you can just number them, which is what we did in the day. So anyway, all of these move at the speed of light. It is all light. Most of it is invisible to you. In fact, if you put this on a scale, if you drew all of these things and you ask, well, how much of this whole electromagnetic spectrum can we see?
Right.
And we see this tiny slice among all these broad zones in the electromagnetic spectrum. We are practically blind.
Oh, goodness.
And we... All right, on the same table, but just put it outside the colors, which is what he did. And he checked the temperature. All right, on the same table, but I wonder what the temperatures are of each of these different colors.
Okay, listen to this.
Look at that. That is...
And you put a sort of slit in the curtains so the beam of light comes through your prism so that it's dark elsewhere except where the prism light goes. And Herschel said, I wonder what the temperatures are of each of these different colors. To even think to ask that.
Yeah.
All right. So he's got a thermometer and he puts it in the blue. And then and by the way, it's an experiment. So you need a control thermometer. So you put the control thermometer somewhere where the colors are not. All right. On the same table, but just put it outside the colors, which is what he did. And he checked the temperature of the blue and the violet and the green and the orange and the red. And he wrote down all of these temperatures. And what he noticed is that the temperature sitting outside of the visible spectrum read the highest temperature of them all.
Right. And now, why didn't he just say, oh, it must be hot in this room? I didn't realize how hot it was in here. Maybe there's something wrong with me. I can't feel heat anymore.
So there it was. And because he didn't put the thermometer somewhere else, he put it
Right,
next
he put
to
it
the
right
other,
next to it.
right next to it, because the same environment is there.
Right.
And he said, "Oh my gosh, there must be a form of light, quote, unfit for vision."
I love the terminology.
Unfit for vision.
Light that
and
is unfit for vision.
And had that thermometer been on the other side of the violet, it's not clear that ultraviolet would have warmed the thermometer in this way. But he happened to have it on the side where the red was, and he discovered infrared light with that experiment. And so when I look at my microwave oven, and I look at a radio transmitter, or I look at my cell phone, and I look at my lamp on my table, it is one happy family of electromagnetic spectrum coming to us.
That's so cool.
It's dope.
Let me just go here really quick. You didn't really get into what I was looking for. Okay, so we have what's called the light spectrum. We may be able to use heat. Now, I don't know, like, exactly. They're talking 2,700 to 3,000 to 600. Let me see here. Yeah, that's really hot. So I don't understand where they come up with these Kelvin temperatures. But it has to do with the black body and temperatures of stars in space. And so there's a curve, and one of the formulas, the UV formula, or whichever the heck one it was, the ultraviolet catastrophe, there's like two formulas, and I don't remember the whole specifics of that. Stars approximate black body radiators, etc., etc., etc. The white star is adjusted to 5270. And then you've got this visible light spectrum, okay? And then you've got the UV and stuff like that. So if we just look at the visible part of the spectrum, it says that the blue color is on the top and the red color is down at the bottom, which is what is this top curve? They've got the white stars down at the bottom. And this is a formula. This is Planck's. What the hell is this? The white star is adjusted to 5270K. Basically, what I want to say is that it's relative. If you think about I don't know why the red is on the right and they're saying it's a cooler temperature. Red is infrared. That should be a warmer temperature. Irrespective. So I'm wondering if heat can be used to manipulate the EM spectrum of, like, because I'm planning on having the EM spectrum hit the, planning on having the blue to the red spectrum from the grating hit the beam splitter, and instead of just having the white light hit the beam splitter. And so, and I want to be able to tune that color, and then so as I do that, I'm wondering if I can affect the colors by adding heat or cool. I want to actually cool the system, not heat it, because heat creates noise. So either way, you could use heat or cool, and so cooling does the same thing. Cooling should affect, you know. But the problem there, then, if I was thinking of cooling the entire enclosure and then let that stabilize, let the temperature of all the windows, the mirrors, the beam splitter, all that stuff stabilize, get rid of all the humidity and the moisture inside and everything. And it would take a long time for that to happen. But once it's done, then you should see changes in I'm looking for changes in the light waves. So colors do have a temperature, and I'm wondering if there's a way to actually measure the temperature as a function of the frequency of the color and use a relative temperature scale in order to affect a particular color. That's sort of what I was thinking. You know, it's crazy. No, there's this one here. This looks interesting. What's this one here? Color temperature. Chromaticity diagram. Yeah, there's something to this, and I really don't want to get involved with this right now.
In the last video, you and I looked at this demo here, where we shine linearly polarized light through a tube full of sugar water, and we saw how it rather mysteriously results in these colored diagonal stripes. There I walked through the general outline for an explanation, keeping track of what questions still need to be answered. Namely, why does sugar water twist the polarization direction of light? Why does that twisting rate depend on the color of the light? And why, even if you understand that this twist is happening, would you see any evidence of it when viewing the tube from the side with no additional polarizing filters? Here, I'd like to begin with the very fundamental idea of what light is and show how the answers to these questions can emerge from an extremely minimal set of assumptions. In some sense, the fundamental question of electricity and magnetism is how the position and motion of one charged particle influences that of another. For example, one of the first things you learn, say in a high school physics class, is that charges with the same sign tend to repel each other. And the strength of this force depends a lot on the distance between them. If your charges are close, that repulsive force is very strong, but it decays very rapidly as these particles go away from each other. Specifically, here's how you might see this written down as an equation, known as Coulomb's law. The force is proportional to the charge of both of the particles, where it's common to use the letter Q. There are some constants in there which alone could not explain. If you wiggle one charge up and down, then after a little bit of a delay, a second charge, some distance to its right, will be induced to wiggle. In other words, when you wiggle that first charge, the direction that the second charge wiggles is always perpendicular to the line between them. And the amount that it wiggles gets weaker and weaker when that line between them is more lined up with the initial acceleration. For the animations I'm about to show, all I've really done is encoded in this one law, which tells us what should this component of the electric field be at every point in space, as determined by the history of accelerations of a particular charge. For example, if I set that charge oscillating up and down in the z direction, and illustrate this component of the electric field everywhere on the xy plane, you see these circular propagations of equal strength in all directions. It's a little easier to think about if we focus on just one axis, like the x-axis. And at first when I made this animation, I assumed that there was some kind of bug, because near the charge it just looks crooked and wrong. But when you think about it, this is actually what you should expect. Because remember, each one of these vectors is supposed to be perpendicular to the line drawn between that point and where the charge was at some point in the past. At points that are far enough away from the charge, which is where this component of the field is what dominates anyway, the wiggling in the field is essentially parallel to the wiggling in the charge. which is why when we think about light waves, we're safe to think about the wiggling direction as being perpendicular to the propagation direction. Like I said, this propagation for just one charge is equally strong in all of the directions perpendicular to its wiggling. And really, I should emphasize that the propagation does happen in all directions of three-dimensional space. It's maybe a little busy to try to illustrate the full three-dimensional vector field on screen like this, so it's clarifying if we just focus on, say, the xz plane. Notice how the waves here are strongest in the x direction, but it still does propagate in all other directions. It's just that that propagation gets weaker in directions that are more aligned with the original wiggling. At the extreme, the only place where there's no propagation is in the z-axis. Because our law has this 1 divided by r in it, the strength of the wave caused by just one particle does decay as you go farther away, in proportion to 1 over r. But notice what happens if I take a whole row of charges, say oriented along the y-axis, and I have them all start wiggling up and down in the z direction, and I illustrate the combined effects that all of them have on this component of the electric field. The effects of all these charges interfere deconstructively along the y direction, but they interfere constructively along the x direction. This is what it looks like for a beam of light to be concentrated along just one dimension. So if you were to focus on the field just a little confusing, and I suspect part of the reason for that is that it's hard to illustrate with a static diagram, but also it's a little confusing when you try to think about the full electric field. For example, here's what the field looks like on the xy plane when I set that little charge rotating in a circle. It's certainly very beautiful, I could look at this all day, but you can understand why it might feel a little confusing. The very last thing I'll mention is that while everything here is a classical description of light, the important points still hold up in quantum mechanics. You still have propagating waves, there's still polarization that can be either linear or circular. The main difference with quantum mechanics is that the energy in this wave doesn't scale up and down continuously, like you might expect. It comes in discrete little steps. I have another video that goes into more detail, but for our purposes, thinking about it classically is fine. Part of the reason I wanted to go through that is because, frankly, it's just very fun to animate, and I like an excuse for a fundamental lesson. But now let's turn back to our demo and see how we can build up an intuition for some of our key questions, starting from this very basic premise that shaking a charge in one location causes a shake to another charge a little bit later. And let's start by actually skipping ahead to question number 3. Why do we see the diagonal stripes? To think about this, you need to imagine an observer to the side of the tube, and then for a particular pure color, say red, if the observer looks in the tube and sees that color, it's because light of that color has bounced off something at that point in the tube and then propagated towards the eye of the observer. Sometimes when people talk about light bouncing off of things, the implied mental image is something like a projectile ricocheting off of some object, heading off in some random direction. But the better mental image to hold in your mind is that when the propagating light waves caused by some wiggling charge reach some second charge causing it to wiggle, that secondary wiggle results in its own propagation. And for the animation on screen, that propagation goes back to the first charge, which itself causes a propagation towards the second. And this is what it looks like in a very simplified situation for light to bounce back and forth between two charges. If you have some concentrated beam of polarized light interacting with some charge, causing it to wiggle up and down, then these resulting second-order propagations are most strong in the directions perpendicular to the direction of polarization. In some sense, you could think of light as bouncing off of that charge, but the important point is that it doesn't bounce in all directions equally. It's strongest perpendicular to the wiggle direction, but gets weaker in all of the other directions. So think about our setup. And for a particular frequency of light, how likely it is that an observer looking at a particular point in the tube will see that light. Again, the key phenomenon with sugar water, which we have yet to explain, is that the polarization direction is slowly getting twisted as it goes down the tube. So suppose the observer was looking at a point like this one, where the polarization direction happens to be straight up and down. Then the second-order propagations resulting from wiggling charges at that point are most strong along the plane where the observer is, so the amount of red that they see at that point would look stronger. By contrast, if they were looking at a different point in the tube, like this one, where the wiggling direction is closer to being parallel to the line of sight, then the direction where the scattering is strongest is not at all aligned with the observer, and the amount of red they see is only going to be very weak. And looking at our actual physical setup, if we first pass the light through a filter showing only the red, we see exactly this effect in action. As you scan your eyes along the tube, the intensity of red that you see goes from being high to being low, where it's almost black, back to being high again. As an analogy, imagine there was a ribbon going down the tube, always aligned with the polarization direction for this color. Then putting yourself in the shoes of the observer, when you look at points where the ribbon appears very thin, you're going to see very little red light. Whereas if you scan your eyes over to points where the ribbon appears thicker, you're going to see more red light. One thing that's nice about this is that if we try it for various different colors, you can actually see how the twisting rates are different for each one of the colors. Notice with red light, the distance between where it appears brightest and where it appears darkest is relatively long, whereas if you look down the colors of the rainbow, that distance between the brightest point and the darkest point gets lower and lower. So what you're seeing in effect is how red light twists slowly, whereas light waves with higher frequencies get twisted more aggressively.
That's the standing wave.
But still, you might wonder why the boundaries between light and dark points appear diagonal. Why is it that how the twisting rates are different and where it appears darkest is relatively long, whereas
meters.
If you look down the colors of the rainbow, that distance between the brightest point and the darkest point gets lower and lower.
0.5 to 0.25 meters. 0.5 meters. Interesting. Let's see here. So, why am I doing it there? .5 meters to inches. That's 20 inches. Holy shit. What's he got, like a 40-inch tube? Are you fucking kidding me? My whole setup is 30 inches long. I don't have room to put a tube in there like that. How the hell did I get that to do that?
In the last video, you and I looked at this demo here, where we shine linearly polarized light through a tube full of sugar water, and we saw how it rather mysteriously results in these colored diagonal stripes. There I walked through the general outline for an explanation, keeping track of what questions still need to be answered. Namely, why does sugar water twists slowly, where if you scan your eyes down the tube, the angle between the line of sight and the wiggling direction changes, and so there will be at least some component of red light scattering towards the eye. So as you scan your eyes from top to bottom, the amount of a particular color you see might vary, say from dark to light. The full demo that has white light is basically a combination of all these pure color patterns that go from light to dark to light, where Lightwave shakes all the charges in the material, specifically circularly polarized light. It turns out that the amount this chiral molecule slows down, say, left-handed circularly polarized light is different from the amount that it slows down right-handed circularly polarized light. Effectively, there's not one index of refraction, but two. Now you might say that seems irrelevant to our setup. Since we are very deliberately shining in linearly polarized light, there is no circularly polarized light. But actually there's a sense in which linearly polarized light is equal parts left-handed and right-handed circularly polarized light. Here, focus your attention on just one vector in this wave, wiggling straight up and down, which is to say, polarized in the z direction. Notice how it's possible to express this vector as a sum of two rotating vectors, one of them rotating at a constant rate counterclockwise, and the other one rotating clockwise.
Pretty crazy, huh?
Adding them together, tip to tail, results in a vector oscillating on a line. In this case, it's a vertical line, but that direction can change based on the phase of the two vectors we're adding together. Here, let me throw up a couple labels to keep track of how much each one of those two vectors has rotated in total, and then every now and then I'm going to slow down that first vector a little bit, and I want you to notice what happens to their sum. Well, every time I slow it down, effectively knocking back its phase a little bit, it causes the linearly wiggling sum to wiggle in a slightly different direction. So if the circularly polarized light wave represented by that left vector gets slowed down a little bit every time it runs across a sugar molecule, or at least slowed down more than its oppositely rotated. The setup here starts with a cylinder full of sugar water, basically, and we're about to shine some white light into it, but before it gets there, it passes through a linearly polarizing filter. And what that means, basically, is that if you look at all of the light waves beyond the point of that filter, those waves are only going to be wiggling in one direction, say up and down. And don't worry, in a few minutes we're going to go into much more detail about what specifically is wiggling and what the significance of that wiggling direction is. But skipping to the punchline first, the demo also includes a second linearly polarizing filter coming out the other end, and I want you to predict what we're going to see once we turn the light on. Now, I suspect some viewers might already have a little bit of a sense for what's going on, because a few years ago, Steve Mould made a really excellent video about this phenomenon of shining polarized light through sugar water. It was really well done, which is no surprise because everything Steve makes is, but even if you watched that, this is a rich enough phenomenon that there's still more to be explained. In fact, even if you made that video, this is a rich enough phenomenon that there's more to be explained. I'm curious, Steve, when you made that video, did you happen to get a good view of the side of the glass, probably when the rest of the lights in the room were off or something like that?
No, I didn't think about the side view.
Great. So given the setup that we're looking at now, once we turn off the room lights and turn on the lamp, I'm curious if you have a prediction for what you might see.
Well, there will be some scattering, I suppose. But then if we're just looking at the tube, we're not applying any kind of filter to just looking directly at the tube. So, I mean, my instinct is nothing. Nothing will happen.
That would have been my guess too. But let me just show you what it looks like when we turn off the room lights and we turn on the lamp.
Ooh.
And then if you turn the initial polarizer, you can kind of see those
Wow.
stripes, those diagonal stripes seem to walk up the tube.
Oh, wow. But why diagonal?
Exactly. Why diagonal?
But why anything? I mean, why anything?
Yeah. Something about the interaction with sugar water separates the light out into these different bands of color. But it does so in this really intriguing way, where the colors appear to form these spiral helixes down the tube. And the other thing I want to draw your attention to is the color that's coming out of the tube after it passes through that second filter. As we rotate the first filter, you rotate through a family of distinct hues. And it doesn't have to be the first filter. If you rotate that second filter, you also rotate through these various different colors. That's Quinn, by the way, who kindly set up this whole demo. And what I love about this setup is that if you want to really understand what you're looking at, with that deep to your bones satisfying sense of what's going on, it requires having very solid intuitions for a number of different fundamental concepts about light, like polarization, how scattering works, and how an index of refraction works. To kick things off, let me show you the overall structure.
I'm getting a little bit too much into this. So he's got 3 months ago, 2 months ago, 12 days. He's got some interesting stuff to. I'll just copy his link there. Let's put it next to that one. I'm just trying to glean some information about the magnetic. That's it, I guess. So light has a temperature. Polarizing the light only affects the electric field. The magnetic field is still there. You don't get rid of one by get rid of the other, but I don't know exactly what that polarizer is doing. All I know is it's affecting a portion of the light that comes back, and whether or not the information I'm looking for is either going to be filtered? Is it going to accentuate the light of the test object, so on and so forth? Can I do something with an intense magnetic field? Actually, one of both, the electric field and the magnetic field, have them exist along the path of the light, understanding how the light goes through in that rotating pattern that they were showing. Understanding that and orienting the affecting field, whether it be electric or magnetic, in such a way that it affects the light coming through. So it would, if you have white light, you've got this. There's also collimated light too, which it seems to me would be helpful. And then we've got the cavity. If we created a standing wave inside the cavity, and then I was thinking about using the slits to tune the cavity inside, and then if we applied an electrostatic field around the cavity, I've got tubes. I got cardboard tubes, but I think we need to. I've also got a bunch of ferrite material, and I've got the idea about running the wires through the ferrite material to intensify the field down through the middle, and how that might affect the light. And I think what I'm looking for is, I may be looking for something that's connected to the light, but not the light itself. And I don't know how to pick off that information. The Theramin program that you connect to the camera may or may not do that. But the other thing that we're going to be doing is we're going to be analyzing the noise level of the light. Something else. So you can use a solar panel. I watched this person use a solar panel and convert the light directly to sound using a solar panel. I haven't tried that. My plan is to use LEDs as a receiver, and so we would have to go through the LEDs and calibrate the LED wavelengths, the transmission and reception of the LEDs. And I had a flashlight that I really wanted to fix so I'm going to solder that light bulb into a variable power supply source, because that light bulb is, it's got a little wire in it. It's more like a heater type light bulb. It's not an LED, it's a flashlight light bulb. So I got a bunch of those, and those all would probably lean towards the infrared side. I also have a black light lamp, and I've got a black light bulb, which I can't seem to find. I've got a green light bulb, I've got a red light bulb. I got light bulbs that are pretty bright in various colors, and I want to use those to try and maybe use that tunable cavity and see if there is something I can do inside the cavity that will cause the strength of the light to get brighter. And I will tell you something that happened in my testing. I was going to use these cheap aluminum strips for my front surface mirrors to reflect to tune my interferometer and set the positions and stuff. Lo and behold, the dot turned into a line. And I tried it against a few other, I've tried to reflect the dot off of some other pieces of metal, and I gotta do that a little bit more. And it seems that no matter what metal I use, fact, even if it's painted, like I got this LED right in front of me. Let's say if I grab this mirror and I reflect, if I reflect the light onto the mirror, I don't want to really reflect that into my eye. I want to use, what about this piece of, what about this white piece of paper here? Let's go, let me go in this, you can't see what I'm doing, but let's see. I've got a metal box that's got red paint on it. And that's a dot. Like everything I'm reflecting this off of. Okay, now I found something. If I reflect that off of, I can't find the actual dot. What the fuck? Oh, it's going through the plastic. Yeah, the light's going through. I'm hitting this metal part of the speaker. Alright, those are dots. But if I grab this piece of aluminum, and actually the razor is aluminum. Let me see if I can reflect it off of that. No, that's turning into a line. If I rotate. I can't do it off of that razor. Oh, I just want to grab this magnet over here with this piece of aluminum on it again. And I can see the dot off of the aluminum, but when I look at the reflection, it turns into a line. Okay. And I can rotate the aluminum, and it rotates the orientation of the line. Shit. Grab this other side here. So I clearly see a dot. Okay, and it's reflecting a line off of on my shirt, like everywhere on my arm. It just shows a line, you know? Now when I rotate this piece of aluminum 90 degrees, the line rotates. So it's weird, you know? Weird shit happens when you practice with this stuff. So, what am I gonna do? How do I proceed? I've got a bunch of lenses that I'm cleaning. What happens if I shine the laser light on my phone? Because he was talking about that material. Let's see if that... Because I'm thinking the aluminum has a diffraction grating on it. I don't know, you know. The phone should have a diffraction grating on it. Oh, that's coming across. There's a couple of dots. Oh, you know what's really weird? It's because inside the light like it's a hologram. So yeah, this because I got a plastic cover on it to protect the phone. Yeah, anyway, there's all that. So I can, what do I want to do? I want to, maybe I can use one of the other lasers that are not as strong, and I want to run that through into this cavity. I've discovered a convex lens which acts like a parabolic mirror, and I can run that. Maybe I can use a white light. I have to use a white light and collimate it somehow and get that light focused onto the convex lens while running the light through another lens that's convex, and trying to get the light to bounce back and forth between the convex lenses, moving one of the convex lenses in such a way that it will create a standing wave of light and cause the light to actually be brighter at a certain point. That would be a number of wavelengths of interference, whatever pattern happening. The reason for being able to see that, if I can see it in a white light, I should be able to see it in any color of light. And also, because when I look at that metal thing, it just reflects off more light than what I'm putting in, you know. So there's the cavity, there's the grating that I've decided to move the grating to the second part, and so I've got to get that grating thing working, and I have to get my light sources smaller and collimated, I think with a lens, so I can get more intensity into the grating. And so I'll have to have a holder for my lenses. So that's what I'm going to work on. Lens holders. I've got to come up with a cavity. I wonder if I should have black material inside of the cavity to bring the noise level down. I think it's a good idea. I don't know how I'd get that black material inside the other thing is like this black material that I got. I don't know if that actually reflects off. It does have some reflectivity, but it's not like it's a dot. Okay, so if it's really close to my hand, there's light there. And I've got some other cloth that supposedly is even darker. Figure out how to make this cavity and see if I can get it to work. And do the grading, and maybe I think what I'll do is I'm gonna move my case over and try to get that camera set up. I don't know how long that USB thing is though. So that means I would have to move my setup. I'm only using one of my processors for music. I could probably move that someplace else, and I could put my setup closer, and that way run it in the other direction, and that way I can connect my USB camera to observe the colors. Yeah, that's the project. All right, I got it. I'm all done. Have a nice night. Sorry I couldn't answer any questions. Sorry there weren't any questions to answer. Such is life, huh?